Dude, we've got some great stuff in this video. Let's see what it's all about. Well, in this video, we're going to be differentiating, then integrating to come up with power series for ln of x and one other really cool power series too. So we'll see what this is all about. This is manipulation at its finest. Is it on the BC exam? No, this is not something you really need to know for that, but is it in a college professor's class? Is it in my BC class? Oh, heck yes, it could be. Let's do this. Let's see math in all of its glory, and power series in all their glory. Write the first four non-zero terms and the general term for the power series expansion for ln x about x equal 1 by first finding the power series expansion of f prime of x. What? So we could use a Taylor series power series expansion, if you will. So we could use the Taylor process for this. It will work. You'll get the same answer. I'm showing you another way of getting the power series for ln x. Let's go. So first we're going to find the power series for f prime. How do we do that? F prime of x is equal to 1 over x. And that is going to be centered about x equal to 1. Now notice that this is of the form a over 1 minus r. And we actually did a problem just like this a little bit ago in video 2. So if you haven't watched that, you could watch it. If you haven't watched it, this is what I did. I took that a over 1 minus r and I crafted this to look like it's centered at x equal 1. That's that home center for ln x that we love. And so we'll go from here. I don't quite have that, right? I don't have the 1 minus. So we're going to make that happen bit by bit, but we want to be centered at 1 first. So to be centered at 1, I can do x minus 1 plus 1. That centers us at 1. The adding of 1 keeps it equal to 1 over x. That's then equal to 1 over, just rearranging things, 1 plus x minus 1. So now we're getting closer to this format, the sum of a geometric series. This is equivalent to 1 over 1 minus a minus x minus 1. Okay, and this, we'll put brackets. That is now a 1 minus r. So now you have that, and I'll put it over here. The first term, which looks like a 9, a is equal to 1, and r is equal to minus x minus 1. Okay, so I usually like to, again, start out with my general template, n equals 0, a r to the n, and I plug in. So a is 1, not even going to show that, and this would be minus x minus 1. I don't know why I put an equal there. So we're going to do that as sigma notation. A is 1, I'm going to leave that out, minus x minus 1, all of that is r. So this is all the r to the n. All of that is r. And that's from n equals 0 to infinity. We're going to expand that out, first 4 non-zero terms in the general term. So that's equal to, well, this is going to be equal to, if I plug in 0, it's just going to be 1, our first term. You multiply by minus x minus 1, you get minus x minus 1. You multiply by another minus x minus 1, you get x minus 1 squared. Multiply by another minus x minus 1, you get minus x minus 1 cubed. Plus dot, dot, dot. And then we go to the nth term, which we know is minus, and it's alternating, so I'm just going to do negative 1 to the n, x minus 1 to the n. You could have also written that term as well. That would work. Okay, first 4 non-zero terms, the general term. This is equivalent to 1 over x, which is equal to the derivative of ln x. So what? Why does that matter? Here's why it matters. The integral of the derivative of ln x with respect to x, right? If we were to take the integral of the derivative, we would get ln x. So then what I'm going to do is I'm going to take the integral of all this. So ln x, therefore, is the integral of this with respect to, what's that with respect to? X. So we integrate this, it's going to be x, more on that in a second, minus x minus 1 squared all over 2, plus x minus 1 cubed all over 3, minus x minus 1 to the 4th all over 4, sweet. And that's your first 4 non-zero terms, plus dot, 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 plus negative 1 to the n, x minus 1 to the n plus 1, all over, and then we'd have n plus 1. And that starts at n equals 0. Now here's the thing. You might be like, yeah, but there's no x minus 1 here. That doesn't match with log. Constant integration, right? If you have this thing centered at 1, when I plug in x equal to 1 into all of these, guess what c ends up equaling to? That goes to 0, that goes to 0, that goes to 0. We're centered at 1, right? And it equals out to 1. Isn't that cool? So we end up with a 1 for C when we plug in, well, 1 for everything. So C ends up equaling -1, I should say, when we solve it all out. So if you plug in, again, 1, all these 0 out, you get 1 plus C, I'll show it to you, equals the ln of 1. So C equals -1. You plug in that -1, and now voila, you've got x minus 1 minus x minus 1 squared over 2 plus, and so on and so forth. It's the natural log. It's another way of getting there. I think I favor using Taylor, but it's a cool way of using the geometric series sum. Finding the derivative's geometric series sum, that is, using that to make a power series, and then integrating it to go back to where we started. Ooh, it's a tongue twister for the brain. All right, we'll do another one. We now know h of x is 1 over 1 minus x. There's the series. Write the first 4 non-zero terms in the general term for the power series expansion for h prime. Okay, so that's not bad because we're given the expansion. H prime is equal to 0, and then derivative of that is 1, plus 2x, plus 3x squared, plus, and then the next term would have been x to the 4th. The derivative of that is 4x cubed. It's the first 4 non-zero terms, plus the general term's derivative, n times x to the n minus 1, and then that keeps on going on and on. That's over that interval of convergence, of course. That's our power series for the derivative. It then says use your answer to find the sum, that sum. And you're like, how the heck am I going to find that sum? I know that it's a converging series because this is going to converge between -1 and 1. Maybe not at the endpoints, but 0.5 falls in the x values where this converges. Wait a second. 1 over 1 minus x is equal to that. Therefore, what that means is h prime of x, even though this wasn't asked for it, h prime of x is also equal to the derivative of 1 over 1 minus x. You might be like, wait, what, why? Let me refresh this idea. 1 over 1 minus x is that. The derivative of this is the derivative of that. We took the derivative of that, which is also the derivative of this. So if I take the derivative of this, it's the derivative of that. Isn't that cool? So the derivative of this is equal to, think about this as 1 minus x to the -1. So that would be equal to the opposite of 1 minus x to the -2 times, chain rule, -1, which is 1 over, that's positive, 1 minus x squared. Ah, so then how do I find this infinite sum? Well, this infinite sum is the same as basically h prime of, notice what we plugged in every time. We plugged in 0.5. So h prime of 0.5 is equivalent to 1 over 1 minus 0.5 squared. Plugging it into the power series form of the derivative is the same as plugging it into the function's derivative. So if you take the derivative of a power series, it is equivalent to the derivative of the function that power series represents. That's killer. Oh, I think it's beautiful. Tough problem. This is the kind of thing I've seen on the BC exam once in a blue moon, but it's been there on free response problems. Maybe in a very tough professor or tough teacher's curriculum. So 1 minus 0.5 is 0.5, square it, and that's going to be 1 over 1/4, which is equal to 4. So that's equal to 4, yo. That's crazy. How do we know it converges to that? It's on the interval of convergence. Why can we not use the power series expansion for h prime above to accurately approximate h prime of 1.5? 1.5 is not within the interval of convergence. So I'll just say because 1.5 is not within the interval of convergence. And I'll just put that in abbreviations for h prime of x. And you might be like, yeah, but you didn't find the interval of convergence for it. I don't need to. I know it's going to have the same endpoints, and 1.5 is outside of that interval. That's it. All right, that was fun. I'll see you in the next and final lesson video before we get into the exercises for this. It's my single most favorite thing that I do in calculus, so you're not going to want to miss it. It's got something to do with pi and, oh, how you've been lied to for many years. Pi has a pattern. Okay, I'll leave it at that. Peace.